Hi everyone. My name is Kun. This is Siji. Our topic today is many birds one stone, exploiting a single SQLite vulnerability across multiple software. It's the first time for us to be presenting at Black Hat. So let me do some self-introduction. We are security researchers from Shaden Security, Shaden Tech. It's a company from China providing pen testing service and enterprise products. We are in the security research team in the company. The team name is Shaden Security Research Lab. We pawned 4 targets in this year's pawn phone contest. And the bugs we will talk today are used in the contest. We also did PS4 jailbreak Android routing in GeekPawn, a smart device pawning contest from China. We are CDF players. We were in the team Bloop last year and won the 2nd place at DEF CON CTF 2016. Next, Siji will start the main topic by introducing SQLite.
Hello everyone, I'm Siji. I think most of you have heard or used the SQLite. It's an in-process library that implements the self-contained, high reliability, zero configuration, and transactional SQL database engine. It is widely used as an embedded database software for local or client storage in applications like the browsers and the mobile applications. This project starts in 2000. It's 17 years old, and it's too old to be secure. If we find any new attack surface or new vulnerability in SQLite, many projects built on SQLite will be affected. There are some previously research about attacking SQLite. As a SQL database engine, it suffers from SQL injection. Here are some examples of the SQLite tricks taken from the SQLite injection cheat sheet. If you are familiar with the SQL injection, you will understand these attacks immediately. Basically, SQLite reads and writes directly to ordinary files. If you can attach any file as a new database and write your web shell. And there's also a special function, a load extension. It can be used to load shell libraries. These 2 methods give you a shell, or usually a remote shell directly. However, they are usually restricted in the real-world cases. So we are more interested in the memory corruption bugs in SQLite. Now we are going to review some public SQLite vulnerabilities in history. As we know, a SQLite database has some tables, indexes, triggers, or views, and they are all contained in a single disk file. The database file format is cross-platform. That means you can copy the same database file between 32 bits and 64-bit system, or move between the Big Indian and Little Indian architectures. These features make SQLite a popular choice for the application format, but they also bring a lot of troubles into SQLite. As we know, it's very hard to write a perfect parser for most file formats. It's the same for SQLite. As you see, these are 2 CVE in recent years. They are describing some issues when passing a malformed database file, and they can cause some heap issues. But in the real world, I think the risk of a heap overflow during parsing the static database file is really low. I think in these two cases are not very likely exploitable in the real world. But luckily, in most cases, SQLite works as an interpreter. It runs SQL statements from the user interactively. This provides a more flexible way for the hackers to trigger and exploit the vulnerability. For example, you can set up a control environment before triggering any heap overflow. These two bugs is triggered in the normal statement of SQLite. The first one is using select statement. The second is happening in create a table statement. But these two are using some weird grammar to trigger the bug. That gives us the idea how to find this bug. If you have enough weird grammar, we can easily fuzz the SQLite and get some bugs. Actually, AFL works very well on SQLite. This page is describing the previous work of another hacker. The author of AFL uses SQLite as his experiment target. It was 2 years ago. He ran AFL for 30 minutes and found 22 unique crashes, including some usage of uninitialized pointers, invalid freeze, or heap or stack buffer overflows. Now, the developers of AFL are also using AFL in their testing strategy. The following example is CV in last page. Is very simple and it's finished in 3 lines of SQL statements. It costs invalid free. But I think if you want some random bugs and report them for CV numbers, you can just run AFL, use AFL to find many random crashes. But if you want to exploit some real-world software, you will need deeper vulnerability and better knowledge of your target. This is the main topic of our presentation. Now we are going to learn some basics about the SQLite implementation details. Every value in SQLite has one of the 5 fundamental data types. They are integers, floating point number, string, glob, and null. They are very simple. And there's also a vector table mechanism in SQLite. A vector table is an object that is registered with any open SQLite database connection. There are callbacks methods for the vector table. They are invoked on the object when you operate on the vector table. This mechanism can be used for representing the in-memory data structures, or they provide a view of the data that is not a SQLite format. For example, they provide a view of JSON or C arrays. And they are more dynamic. They can be used for computing the content of the application on demand. There are many features in SQLite. The features are introduced as extensions. Most of them are just implemented as vector table. There are 2 interesting vector tables. FTS 5 or 3 is for full text search indexing, and R3 module. R3 is a special index is designed for doing range queries. We will discuss them later. Now you may find the problem of SQLite. Some extensions like FTS3 or R3 modules require complex data structure. They have some internal data that are stored in the same database. As we know, there are only 5 types of the fundamental data. So the internal data can only be stored as the blob type. Now here's the questions. How can we know the original type of the blob data? And should we trust the stored blob data in the database? Actually, we can find the answers by reading the source code. From reading the source code, we learned that the developers of SQLite don't like checking the types. In comments or the documents, they just assume a variable with special names is always associated with special types. They just trust the column name or the function argument name and everything else from the database. Now we are going to review FTS3 related bug in SQLite. It's reported 2 years ago, but there are not so many people researching on it. It's a bug in FTS3. Actually, I don't think most people using SQLite will use the extension. They are modules that allow users to perform full-text searches on set of documents. From my understanding, they just provide the algorithm framework, and you have to use your own tokenizer to process the documents. Or you can just use the default tokenizer that is called simple. And they also provide other tokenizers. FTS provides an interface for the developers to implement their custom tokenizers, which is written in C. But FTS does not provide a C function to allow users to register the tokenizers. Instead, you have to encode your pointer to your own tokenizer in a blob. That is just a raw data. Then you can pass the blob to the engine through the SQL statement. You need to use a special Scala function that is FTS3 tokenizer. FTS3 tokenizer accepts 1 or 2 arguments. The first one is the string of your tokenizer's name. The second one is a blob, which is used as a pointer to a tokenizer module. If there's only 1 argument, the query returns the address of the registered tokenizer, which is in blob. If there are 2 arguments, the query registers a new tokenizer with given parameters. Actually, there's no guarantee for the type of the blob in the SQL statement. So it could be very dangerous if you just pass and dereference a pointer in SQL queries. Here's the POC of the old bug. It is very simple and elegant. The first query leaks a pointer to internal structure. It's the tokenizer simple. The second query registers a new tokenizer with some random address. The new tokenizer is my tokenizer. Later we can create a virtual table using FTS3, my tokenizer, and they will use the invalid address to look for some invalid callbacks. That's memory corruption. The third query shows that we have successfully registered the new tokenizer, and it's stored in the database. To summarize the bug, it's a very powerful bug. First, it gives us the ability to leak the address information. It returns the built-in tokenizer, and it leaks the base address of the SQLite module. It also dereferences any untrusted pointer. It's a very powerful memory corruption. The misuse of FTS3 tokenizer can help us to bypass ASLR and dereference untrusted pointer. That's enough for most exploitation. As I said, the vulnerability has better quality than any other previous SQLite bugs, and it can be exploited through browsers. Before porting the bug to browsers, we have to know how to use it in the browsers. Basically, there's a API web SQL database. It's a web page API for storing the data in database that can be queried through the SQL language. Actually, the specification has been stopped maintaining since 7 years ago. But many modern browsers like Google Chrome, Safari, and Opera have an implementation based on SQLite as the backend of web SQL database. Here's an example of using SQL in the browser. Actually, you are just writing SQL in JavaScript. From the color text, you can learn how to use the web SQL. Basically, you open a database with your name and version and memory limit, and you start a transaction and put a callback in the transaction and execute your SQL statements. Then you also have another callback that handles the result of the SQLite SQL queries. But not all SQL statements can be executed in the browser. For example, this is the code from the WebKit. WebKit has a SQLite database authorizer to check if you are allowed to perform certain SQL statements. For example, if you want to create a virtual table, they will check the module name of your statement. Only FTS3 is allowed virtual table in WebKit. And there are more restrictions for functions. There's a whitelist of the functions. Every time you invoke a function, they will check if it's a whitelist function. For example, FTS3 tokenizer, the target function is not on the whitelist. But we have another bug to bypass the restriction. Actually, this CV is reported with the previous one to ZDI at the same time. The idea is very simple. For the vulnerable SQLite, it does not check the default value of an uninitialized column. We could create a table with expressions like FTS3 tokenizer simple. They call the privileged functions. The expression is evaluated when we insert a new record into the table. Then we can read the result back from the database. So in this example, the red text are the where we could insert the privileged call to the dangerous functions. From this code, we can leak the base address of SQLite module in the browsers. Now, exploiting the bug in the browser is kind of trivial. ASR is already bypassed. You just need to spray a lot of memory and dereference and jump to your option. Actually, we use the bug in our private PS4 jailbreak because they are using WebKit. And we exploit it blindly. Now we are going to discuss exploiting the bug in PHP. For many cases, if you have a web share on some website, you want to but you may find the admin set the disable functions to restrict your ability for future pen testing. These disabled functions are restrictions in PHP. But if you have the native code execution, the then you are not in a real sandbox. You can get a shell by exploiting the bug in SQLite. There are more details exploiting the bug because libphp and libSQLite 3 is not the same shared library. You might need to reconstruct the same environment with the remote server. You can use the leaked information from PHP info and build same environment and test your exploit. There are more details about exploiting PHP. Basically, you will trigger some callbacks in the faked structure. We found there's a callback xopen that takes one argument from the SQL statements. Then you can find a gadget that points to popen or a system that can directly return a shell for you. Or there are many other tricks you can. Since we know SQLite is processing a database file, if you open the path with column, memory, column, then all the operations are done in the same memory. You can use that to spray your structure. Now we are talking about what the reactions of the other vendors. Actually, Android has a custom branch of SQLite. The Android team has noticed the risk of FTS3 tokenizer, and they disabled it 3 years ago. It's happened before the report of the previous bug. And the developers of SQLite also noticed the risk of the tokenizer. You have to compile SQLite with a special option before using it. The WebKit also has its own patch for the bug. They have a blacklist of the dangerous functions. The blacklist prevents hackers from calling the bad functions even if they have bypass of the whitelist. The patch reveals more interesting functions. There are functions R-tree node and R-tree depth. That is even uncommon than the FTS3 tokenizer. It tells us where to find the interesting functions in SQLite source. So this is the source of the R-tree node function. It takes 2 arguments. The first describes the dimension of the R-tree node. The second argument is just the R-tree node value. There's no check in the function, and it can be used for out-of-bound access. But it's not as dangerous as the FTS3 tokenizer. But now we know we should find more bugs in R-tree module. So here's the freezer day for you. In the function deserialize geometry, a blob in a special structure is used as the operand of the match expression. The developers knows that if you operate on the invalid blobs, could cause a segfault. And then he wrote the idea in the code. To solve the problem, he used a magic value in the beginning of the blob. If all the sanity checks passed, a function of the function pointer will be loaded from the blob. That is the p blob. The text in yellow is p blob cbx geometry. You can have PC control in 3 lines. First, you create a vegetable in R-tree and insert some values into it. Then perform a select statements using the match expression. The line starts with X means it's a blob. The AB451289 is just the magic number in the source code. And if you run the 3 lines, you will get directly PC control and RDI control. Did you take a picture? this page is not available in the public sites. Okay. You should remember the R3 virtual table is not available in the browser. The only one is allowed in browser is FTS3 virtual table. We prefer the explore the bugs in browser. So we start looking for bugs in FTS3. If we check the function whitelist, we can find some functions that is rarely used, but it's still in the whitelist. For example, the optimize is a function that is for special FTS3 operation. I don't think any of you have knowledge about how to use the function. In the code, it extracts the FTS3 cursor variable from the first argument. It calls the FTS3 function arg. It's the code in black. The code FTS3 function arg does very simple job. The SQLite value type returns the type of the value. It has to be a blob. SQLite 3 value bytes returns the length of the value. It must be a size of a pointer. If these checks are passed, then the blob will be parsed as the FTS3 cursor. Now let's have a quick review of the virtual table mechanism. The virtual table can have a custom method, xcolumn, to find the value of the nth column of current row. In FTS3 virtual table, it accepts the table name as the column name. Some functions, like optimize, take the table name as the first argument. Basically, what you should do is just select optimize T from T, where T is the FTS3 virtual table. During the execution, column T stores the current FTS3 cursor. In the execution of SQLite, the SQL statement is prepared and compiled into bytecode, and then evaluated by the SQLite engine. For this case, the type information of the column is already lost, and the interpreter can never know the required type of this column. Now this is another POC. I will create a virtual table in A, and it has only one column, FTS3. The only column is B. Then if we select hex A from A, using the table name as a column, it leaks the address of a heap structure that is the original FTS3 cursor. If we optimize B from A, then B is used as the FTS3 cursor, which causes the type confusion. Okay, now we are thinking about how to exploit the bug. Now Quinn will teach us how to exploit the bug.
With the exciting bugs in hand, it's time to think about how to exploit them. Let's take optimize function as an example. The source code of the function is on the left. pCursor is a pointer of struct FTS3 cursor. The function FTS3 function arg will resolve the first argument of optimize and fill the result into pCursor. With the type confusion bug, in FTS3 function arg, we can specify arbitrary value for pCursor, so that we can dereference the struct FTS3 cursor in some arbitrary address, like in the POC in this slide. The pCursor will be dereferenced at 414141, 424242. So that is to say, if we can control memory in some known address, we can fake a FTS3 cursor there. From the code lines colored with blue, P is derived from P cursor and points to struct FTS3 table. So this FTS3 table can also be constructed in controlled memory. The following function, SQLite 3 FTS3 optimize, will handle the fake instance of FTS3 table. FTS3 table is a complex struct with members of pointers and substructures. So we started to do more code review to see if we can achieve memory read-write primitive or PC control through some code path. So here is the summary of our exploitation strategy. In most of the modern browsers and operating systems, we can still use heap array to have memory control in some hard-coded address. For example, by allocating a lot of array buffer objects, we can fake FTS3 cursor, FTS3 table, and other related substructures. Those vulnerable virtual table helper functions like optimize, offsets, match info will handle our constructed structs. Through some specific code paths, we have memory rewrite and PC control. So in the following slides, we will show some exploitation paths that we used. But it's also possible to find other code paths to achieve the same results. So on this diagram, it demonstrates one path for upstream rewrite primitive. In the last function, it is SQLite 3 VDB memSetString. This function is basically just doing string copy with controlled source and destination. By using this function, if we just do copy data from some controlled location to any other address, it is just doing memory write. On the other hand, if we use this function to copy data from any other address to some controlled location that we can read back, it is just doing memory read. So since it's a long path in the previous diagram, we're going to go through it to show how we constructed all the structures. On the right side, there is a diagram showing how we construct the structures and their members. Currently, we have constructed a FTS3 cursor and added a FT3 table in it. The next step is to see what the highlighted function, SQLite 3 FTS3 optimize, does, and how we continue to build the FTS3 table in the diagram. Inside SQLite 3 FTS3 optimize, it will invoke SQLite exec. If SQLite OK is returned, then it will take the if-then branch and execute a lot of code. But our interested function is the highlighted one, SQLite 3 FTS3 segments close. So there is nothing to do with the if-then branch. So we'll want to try something to make SQLite exec not return SQLite OK. By looking at the code of SQLite 3 exec, we can see that if db equals to 0, the function on the right side, SQLite 3 safety check OK will return 0, and then SQLite 3 exec will return SQLite misuse bkpt. It's not SQLite OK, so our goal is achieved. So in this diagram, we are showing the construction procedure for structures. We set db in FTS3 table to 0 in this step. Now let's move on to the function SQLite 3 FTS3 segments close. It's calling SQLite 3 blob close and passing pp segments. pp segments point to a struct incra blob. So we also added this struct to FTS3 table. In the function SQLite3 blob close, two more structs are referenced. Look at the first one, the variable db colored with purple. It's a struct of SQLite3. SQLite3 is a type for describing database connections. So we add a SQLite3 to include blob. And there is the function SQLite3 mutex enter for synchronization. By setting mutex to 0, we can survive all those mutex related functions. The second new struct added here is p statement, colored with green. It's a struct of VDBE. VDB is a type for describing SQL virtual machine. So we also added here because the SQLite finalize function will handle our constructed VDBE. On the left side is the source of SQLite3 finalize. The interesting function here is SQLite3 VDB finalize. To reach the function, we have to survive the other function calls like VDB safety, check profile callback. I'm omitting some details here because it's not very hard. You can just set some members of VDBE, and then you can survive all these functions. So let's move on to the function on the right side, SQLite3 VDB finalize. By setting pmagic to VDB magic hot, we can reach the interesting function SQLite3 VDB reset. So for the moment, we have built 5 structures and they are connected as the way showing in the picture. The condition highlighted with green is added in the last step. Let's move further. In SQLite3 VDB reset, the VDB's member PC is examined for different branches. We set PC to 0 so that we can take the first branch and go into the function SQLite3 VDB transfer error. So in the diagram, we added the new condition, PC greater or equals to 0. Now in this slide, the function SQLite3 VDB transfer error will call SQLite3 value set string and then call SQLite3 VDB mem set string. This function is the aforementioned string copy. So we are close to winning. Looking at the function called SQLite3 value set string, there are 2 important arguments, the red dbp error and the green pd error message. dbp error is a new struct, so we created pd error message is simply a say style string pointer. According to the check in the if statement, we should specify a non-zero value here. So in the last line of the code, we can tell that both dbp error and the error message will be handled in the function SQLite3 VDB mem set string. This function exposes all the secrets of arbitrary read-write primitive. The key function of doing string copy is mem copy. Let's pay attention to the mem copy. The source of mem copy is they, which is highlighted with green. They comes from the VDBE's the error message. The green, the error message. They is just a say style string pointer, so we could specify any address to be the source of mem copy. For mem copy destination, it's pmem day. Pmem is a struct of mem, which comes from DB's member p error. We also mentioned this in the previous slide, the red one. The struct mem also can be constructed so that we could control destination pointer pmemday. But pay attention to the function SQLite 3 VDB mem clear and resize. This function will assign pmemday to the value of pmemday malloc. So in the final, mem copy's destination is controlled by pmemday alloc in orange. The copy length is nalloc. Nalloc equals to n byte, and n byte equals to the length of day, which is the source string. So that's why we say SQLite 3 VDB mem set string is basically doing string copy. To conclude, by constructing the 6 structures with proper members, we could achieve arbitrary string copy primitive, which is equivalent to read-write primitive. The source of string copy could be specified in the malloc, and the destination can be specified in the error message. So arriving at this point, with arbitrary read-write, we almost can say we are done, because it's been well studied to play with JavaScript objects with read-write primitive. But if we want to remove platform dependency as much as possible, we better find some way to execute code with SQLite, because the implementations of JavaScript in different browsers are different. Luckily, it's not very hard. If you dig into structures in the source code of SQLite, you could find many callbacks. There are many code paths from vulnerable function that ends with callbacks invoking. We used this path in the diagram to have PC control. The last function is invoke profile callback. This function will invoke many callbacks like xProfile, xTrace, xCurrentTime, xCurrentTime int64. These callbacks can all be controlled in the structures that we built in SQLite memory. So in this invoke profile callback function, it will first call SQLite 3 OS CurrentTime int64. This function will invoke xCurrentTime callbacks, and then xProfile and xTrace will be invoked. We prefer to use the callback of xProfile here because we can also control 2 arguments here by controlling db, pProfile_arg, and pTheSQL. But to reach xProfile, we should survive the function SQLite 3 OS CurrentTime int64. But this is easy. This just can be done by simply notify the xCurrentTime callbacks in db pvfs structure. So this diagram is showing how we create the structures to achieve arbitrary function call. PC is controlled in xProfile, and the 2 arguments are controlled in pProfile_arg and TheSQL. So it's time for us to defeat ASLR. ASLR is everywhere in modern targets. Let's review the information disclosure bug. We could use it here because by this bug we can leak the address of some FTS3 cursor struct. By digging into the details of the struct, we find that the first member is pointing to a global variable in SQLite. It's called FTS3 module. So by read primitive, we could read the address of FTS3 module and leak the address of SQLite library. In some targets, SQLite is statically linked together with other libraries so that we could use more gadgets and functions. As with shellcode execution, we could use function called primitive to invoke method like mprotect to have executable memory. We can also use long jump to turn function called primitive into RUP, because we can change the RSP in long jump gadget. So in this slide, these are some birds that we could hit by using the stone of SQLite bugs. So we bring some demo here.
先退出原名吗？先退出原名。
So this is demonstration of bypassing PHP security restrictions by using the bug of tokenizer. With remote PHP code execution, we can use the vulnerability to execute arbitrary code and get a reverse shell. The second demo is a Pontoon-style exploitation, targeting suffrage. By using the new bugs of SQLite, we can get remote root by visiting some malicious website. And now we have root. So due to some timing problem, we will skip the two demos targeting WeChat and Alipay, because they are just similar with the browser attack. So it's time for QA. Sorry, I cannot hear clearly.
Are you because we use another sandbox bypass to get a root.
Yes. This exploitation is combined with another bug. So no questions? Thank you, guys.